we're going to pick up today where we left off last time, which is with acetal formation and hydrolysis. I just want a brief review of acetal formation because I want you to see what we're talking about today as different manifestations of the same theme. And the theme is we're going to use an acid catalyst. Oh, I get to take this off now. Haha. We're going to use an acid catalyst to change who's the good leaving group on the tetrahedral intermediate. So recall in acetal formation, the neutral alcohol is not a good enough nucleophile to attack the carbonyl carbon directly. So we first must protonate the carbonyl oxygen. That generates an oxonium ion that's more reactive. And now the neutral alcohol can attack. When you do that, you get a tetrahedral intermediate. And at this stage, we start asking who's the good leaving group. Right now, it's the methanol group that just barely attacked. And it would be perfectly reasonable for this oxygen to, on the OH group, neutral oxygen, to kick down and kick off that leaving group. Doing so would take us back to the previous step. But if you look where we're trying to get, we need to get rid of that OH group and replace it with another methanol group. So what we do is we use our acid catalyst to remove the proton from our methanol oxygen. That turns it into a neutral ether type oxygen. And now we have an intermediate where there isn't a good leaving group. This intermediate has a name. Your text identifies it for you, and I'll point it out now. It's called a hemiacetal. Hemi because it's halfway to the acetal. We've replaced one of the carbon-oxygen bonds with a bond between carbon and the methoxy group. Hemiacetals are generally not stable because in acid catalysts, they're higher energy than either the aldehyde starting material or the acetal product. And so in the presence of acid, they will go either to here or here. They can also fall apart in base. We won't talk about that or worry about that. Hemiacetals are generally not stable. There is an exception to that. If the hemiacetal can be cyclic, it can be somewhat stable. That's important for carbohydrate chemistry, and we'll talk about that a little bit later today. We then use the acid to protonate the OH group, thereby converting it into a good leaving group. Now the neutral ether or methoxy oxygen is strong enough to kick down and remove water as a leaving group. We talked last time about how you can drive this equilibrium forward by removing water, which promotes product formation. When water leaves, we're left behind with another oxonium ion. The difference between this and the other oxonium ion we encountered earlier is that this oxygen was positively charged because it was protonated. This oxygen's positively charged because it's, in addition to the pi bond and the sigma bond here, it's bonded to an alkyl group. At that stage, neutral methanol can attack to generate this tetrahedral intermediate. Again, that methanol that just attacked is a good leaving group, but we can change it to not a good leaving group by removing a proton, and that gets us to the acetal product. Okay, so using proton transfer to swap who's the good leaving group, all of these are equilibrium steps. We drive the reaction forward by removing water. Okay, any questions you want to ask about that? Okay. So acetal hydrolysis, starting from this product, actually has the same intermediates all the way back, only we're going to push the arrows in a different direction. We're going to do acetal hydrolysis using hydronium in water. And when we say hydronium in water, that could be using aqueous HCl or any other aqueous acid. The excess of water is going to push our equilibrium back from the acetal to the aldehyde. Now, I will just mention, we are going to talk about why on earth you'd want to do this and why acetals are important. Turns out acetal chemistry is essential to understanding carbohydrate chemistry and metabolism. And what we learn from acetal chemistry is also going to inform some considerations later on in this class where we talk about why it's bad to have high blood glucose and what glycated hemoglobin is. In any case, if you compare what we're doing here, the intermediates are exactly the same. So, starting with the acetal, if we want to get back to the aldehyde, we need to replace both of these two carbon-oxygen bonds with a carbon-oxygen single bond and a pi bond. To do that, we're going to need to convert one of the methoxy groups into a good leaving group. So starting with the acetal and the acid, we simply protonate one of the methoxy oxygens. That gets us to this previous intermediate. Okay? Then the neutral oxygen can kick down and remove methanol as a leaving group. That gets us to this oxonium ion. And go back and convince yourself that this is the same intermediate as we saw above. Then, instead of methanol attacking to go here, we have water attack to give us this intermediate. Again, water is the good leaving group here, but we can change that by having the conjugate base of our acid catalyst remove a proton. That stops the OH2 group from being a good leaving group, and that gets us to the same hemiacetal intermediate that we encountered before. Now we have no good leaving groups on our hemiacetal intermediate. We want ultimately to get rid of the methoxy group, so we're going to need to convert it into a good leaving group. We can do that with the acid catalyst. That generates an intermediate that we've already drawn above. In this intermediate, the positively charged methoxy group is the good leaving group, and the neutral oxygen can kick electrons down and kick the leaving group off. Methanol is our leaving group. And what's left behind is this oxonium ion that is only different from the aldehyde in the presence of that proton on the carbonyl oxygen. And we can get back to the aldehyde by regenerating our acid catalyst by removing the proton on that oxonium ion. So, what I've seen students struggle with in the past is just in a mechanism, how do I know which oxygen gets protonated? And the answer is somewhat like the Cheshire Cat's answer to Alice in Alice in Wonderland. Which path do I take? Well, it depends on where you want to end up. And if you don't know where you want to end up, it doesn't matter which path you take. All of these things are happening in equilibrium, forwards and backwards. We're controlling the direction by our reaction conditions. If we remove water, we go forward. So you need to have a sense for what you're going to accomplish when going from aldehyde to acetal. That guides you in terms of your choices. You protonate the oxygen to make it reactive enough, methanol attacks. You want methanol to stay, so you need to change who's the good leaving group and so on. In contrast, if your goal is to hydrolyze the acetal back to the aldehyde, you need to turn the methanols into a good leaving group. Okay? So you may want to practice that backwards and forwards until it makes intuitive sense to you. All right, anything else you want to ask about that? Acetal formation and hydrolysis. Yeah?
Can you just explain again why removing the water in the first mechanism pushes it towards the product?
Why does removing water push towards product formation? Le Chatelier's principle says that, and the reason this works is, a reaction's at equilibrium when the forward rate and the reverse rate are the same, right? If you decrease the concentration of one of the products, that slows down the reverse rate, and then the forward rate wins. Yeah. Okay, yes?
Just reviewing why in the formation of acetals we were using ETSOH as our acid.
Right, why were we using this as our acid? We don't want to use water because we need to remove that as a product, so we need an acid that is organic soluble. This happens to be one of them. You could use, as an alternative, you could use acetic acid. And sometimes that's done, that's soluble in organic solvent. So it's not only this one that works, it's just an organic soluble acid. You don't want water around. Yeah. In contrast, anything will really do down here as long as it's in water. Hopefully you're comfortable with the idea that if I draw H3O+, I'm assuming there's a counter ion there. If it's Cl-, that was HCl. You don't just open up a bottle of H3O+. There's no such thing, okay? All right, other questions? Okay, so let's talk about acetals and hemiacetals in biology. And there's going to be structures here. There's going to be a lot of chairs. The question that students often ask, they get distracted with, do I need to memorize this stuff? Clearly not, right? You won't be drawing any structures from scratch on an exam. You don't necessarily need to memorize the structure of glucose yet. That will happen later in a carbohydrate chapter, but I want you to focus on the chemistry and the functional groups. So glucose, if you didn't know this, is an aldehyde. I'm going to draw this aldehyde in an interesting way that's going to make sense in just a little bit. Glucose is a 6-carbon aldehyde. It's called a carbohydrate because its molecular formula is C6H12O6. For every carbon, we have one H2O, carbohydrate. But in solution, this open chain form, sometimes people call this open chain glucose because of what happens next. Oh, that's not an equilibrium arrow, is it? Notice the key functional groups in glucose. You have an aldehyde on carbon 1, and then you have 1, 2, 3, 4, 5 OH groups. And it turns out this OH group on carbon 5 can attack the aldehyde carbon through acetal formation. Now, I'm not going to draw that mechanism. Presumably, you would need some acid to protonate the oxygen first. It turns out that H3O+, the limited amount of H3O+ that's present in pH 7 water is sufficient to make the following molecule, where we're going to take the oxygen on carbon 6 and bond it to the carbonyl carbon 1 to get the following structure. And this is a hemiacetal. So we brought this oxygen on carbon 6 and bonded it with carbonyl carbon 1 to give us this hemiacetal functional group. Now, students in general, as I've noticed in the past, get distracted by rings. I feel like you see a ring and immediately your brain is like, oh my gosh, what do I do? That's why the skill you want to develop is the skill to take a deep breath and focus on the key functional groups. Notice that if I draw the molecule this way, it suddenly looks a lot more friendly, right? That's a hemiacetal. Now, I told you hemiacetals are not stable, but this one can form a cyclic 6-membered ring. And therefore, its stability goes up, and it becomes the major product or the major form of glucose in aqueous solution. Notice that this acetal or hemiacetal carbon is a stereocenter. It turns out that you can form the other stereoisomer in which that OH group is up. We'll learn more about that later. These two molecules are diastereomers of each other because they're only different at one stereocenter. Instead of, you can use R and S for that stereocenter, but carbohydrate chemists don't. When the OH group is up, they call it beta. And when the, oh, goodness, I just drew the same thing, didn't I? Was nobody going to say anything? You're just going to let me go on and do that? Come on. Friends don't let friends screw up stereochemistry, right? When the OH group is down, we call that the alpha diastereomer. And they both actually exist in equilibrium with each other because you can imagine that depending on whether the aldehyde is flipped this way or with the oxygen down instead of pointing down and the hydrogen over here, you could get either stereoisomer. Okay, so that's a hemiacetal form of glucose. Let's talk about glucose and acetals. Notice that we've only replaced one of the original carbon-oxygen bonds with an OH group here. We still have that OH there. And also notice that glucose has a ton of other OH groups. So now we're going to imagine what happens when we take a hydroxyl group from one glucose molecule and have it replace this OH group on another glucose molecule. And what do we get then? So let me show you sort of how this is done. We'll start, and I'm going to draw all the intermediates in their complicated glory because afterwards I want you to go back and sort of draw them in simplified form like I've done here and convince yourself that there's nothing going on here that you don't understand. Remember that when we were forming acetals and we got to the hemiacetal stage, we needed to turn the OH group into a good leaving group so that it could leave and generate an oxonium ion. So the first step is to use some acid catalyst, perhaps an acid that you add, perhaps an enzyme to protonate the OH group. I'm going to just start there because I'm assuming that you know how to do proton transfer. We good? Okay. Then what we did with that intermediate was we had electrons on the neutral, oxygen kick down and kick off water as the leaving group. We're going to do exactly the same here. What's generated then is this cyclic oxonium ion. Positive formal charge on oxygen will fill in the other OH groups. One of the great things about glucose is you can remember its structure because everything's equatorial, except perhaps the stuff on carbon 1. This oxonium ion is exactly analogous to the oxonium ion we drew previously. Okay. At this step, remember above we had methanol attack as a nucleophile. Here we're going to have another sugar, another OH group on another carbohydrate molecule. In this case, it'll be two glucose molecules. And how do you know which one reacts? Well, if you are biology, you have an enzyme to control that. Maybe the enzyme grabs a hold of the glucose molecule in such a way that only one of the OH groups is accessible. If you're in the lab, you have to do some elaborate protecting group chemistry to protect this one and this one and this one and maybe that one, but not that one. And that's actually pretty tricky. The Savage Lab here at BYU is world-class expert at that type of chemistry. They're really good at it, and it allows them to do some really neat things in chemical biology, but it's tough, and it takes people, their whole PhD to do it properly. But if you want to learn how to do that, go join the Savage Lab. You can't get better training in the world on carbohydrate chemistry. what happens in biology for the carbohydrate that we want to make is this OH group on carbon 4 acts as the nucleophile, and it attacks the oxonium ion. I'm going to show it here attacking from above. It could attack from below. We're using, the enzyme is controlling the orientation of attack. So you're going to like this, because now we get to draw multiple chairs. I think if you hate drawing chairs, there are stencils available to you, but rather than buy the stencil, just learn to draw the dang chair, okay? If you struggle with that, come talk to me, I can help you. Will you ever need to draw a chair again in your life? Yes, when you're telling people the chemistry joke, which is the OChem joke, which is what is the opposite of a chair? And the answer is the other chair. That's how you, that's the secret passwords by which you identify other nerds who've taken this class. Try that one as a pickup line, right? Okay, so we can use then the conjugate base of our acid or some enzyme functional group to remove the proton, and that gives us a disaccharide in which we have linked one sugar to the other via an acetal linkage. Where is the acetal? It's right here. And you could redraw this as just lots of R groups. And 3 little marks, yeah. That's what we're looking at here, okay? Now, this would be called a disaccharide. It's also called a glycoside. And the biochemists and cell biologists will not call this an acetal linkage. They will call it a glycosidic linkage. This isn't important for this chapter. It will be important later on in our carbohydrates chapter, but this particular glycosidic or acetal linkage links carbon 1 of one sugar with carbon 4 of another sugar, so it's called a 1,4 linkage. And the stereochemistry at carbon 1 has the oxygen up, which is beta, so that's called a beta 1,4 linkage. You might have seen that before. This might be new. You'll encounter it again in biochemistry. So, big deal. Who cares? Well, it turns out you can stitch multiple glucose molecules together in a really, really long chain if you repeat this reaction again and again and again to have another sugar here. Oops. And another sugar there with the same types of linkages. This is the carbohydrate cellulose, which is used in plant cell walls. But you know it better as fiber. So now you know, if you didn't already, why fiber shows up under the carbohydrates label in food labels. It's not that you get any calories from fiber, it's just that it is a carbohydrate, so that's where it fits. Why don't you get any calories from it? Because your body does not have the enzymes to break apart this beta 1,4 linkage between glucose molecules, which is why we don't typically eat grass, and which is one of the reasons why why vegetables are considered so healthy, because you can eat a lot of them without accumulating a lot of calories. They do contain important vitamins, minerals, and so on, but one of the big things about them is you can eat many, many, many cups of lettuce without, if that's your thing, I don't know, without getting a lot of calories. Fiber goes in, fiber comes out mostly unchanged. Now, there are organisms called ruminants that can eat grass, cows, sheep, and the reason that works for them is that their gut microbiome has the right bacteria to break apart that linkage, and then they can gain nutrition from it. Cows have multiple stomachs because this process takes a lot of time. Okay, well, we do get our glucose from food, but the form that works for us is not the beta-1,4 linkage, but the alpha-1,4 linkage. So notice in this carbohydrate that I'm drawing, we have taken the acetal carbon 1 on one sugar and linked it to the OH group on carbon 4 of the other sugar, but we've done so, I need to fill in the OH groups before we go on. We've done so with alpha stereochemistry. The oxygen on acetal carbon 1 is down instead of up. That's an alpha-1,4 linkage, and this is the structure of amylose or starch. So that minor difference in stereochemistry, you do have an enzyme that hydrolyzes this linkage. Some of it's in saliva, so you want to do the hydrolysis reaction now. You stick a saltine in your mouth or some other kind of cracker and you suck on it for a while, and you may start to taste some sweetness, which is some liberated glucose molecules. Just don't, if you're going to do that, don't do it necessarily in public, because sucking on a saltine is just kind of gross. It's kind of a gross thing to do. All right, so you do have the linkage you do have the enzymes to hydrolyze that particular kind of linkage. One other carbohydrate that might be interesting to talk about, because it has a lot to do with human history and evolution, and it's a thing that affects us today, is the following disaccharide. This is a disaccharide that has a beta-1,4 linkage between a glucose molecule here on the right, and then on the left is something that resembles glucose, except the OH group is up on carbon 4. This is still a beta-1,4 linkage. This sugar is glucose. This one's called galactose. The galact part comes from the Greek word for milk, same word that we use in our word galaxy because of the Milky Way. This is a sugar, a disaccharide that's present in milk, dairy products, right? Lactose. So the human infant expresses an enzyme that can break apart this particular linkage, this beta-1,4 linkage, and that enzyme is called Beta-Galactosidase. This is a glycosidic linkage. This is the galactoside of glucose, and beta-galactosidase, A's enzymes are things that hydrolyze linkages. So the human infant can break apart that linkage into the component sugars, but early on in human history, humans stopped drinking milk after they stopped nursing in childhood, and so there wasn't a need to hydrolyze, to break apart lactose, and so beta-galactosidase expression in the intestines goes down. Now, if you don't express beta-galactosidase, you can't hydrolyze this linkage, but your gut microbiome can, and that can result in gas and bloating and all of the other uncomfortable symptoms that are associated with lactose intolerance. So why are some of us lactose intolerant and others aren't? There's an interesting genetic story in human history. The genetics indicate that humans migrated out of Africa thousands and thousands of years ago. Some of them went into Asia, others went into Europe, and at some point in Europe, a mutation occurred that allowed beta-galactosidase expression to persist. into adulthood. And scientists hypothesized that the reason this was selected for and became a selective advantage was because it allowed people to continue to get nutrition from dairy. Now, we're not talking about nursing into adulthood, but we're talking about agriculture, right? Converting cow's milk into cheese, which cheese you can store indefinitely, right? Milk goes sour within days if you don't have refrigeration, but cheese and butter you can store indefinitely. And so being able to gain nutrition from that was an advantage. And so if you have European ancestry, chances are you're not lactose intolerant. If your ancestry isn't from Europe, chances are, or if you're from Asia, Africa, other parts of the world, chances are you are lactose intolerant. Fortunately, all of us can enjoy ice cream today because you can take some beta-galactosidase in pill form, or you can drink milk that's already fortified with beta-galactosidase, and then you don't experience the symptoms. Go ahead.
Speaking of milk that's already fortified, why doesn't it break down the milk in the carton?
You know what? I'm not actually even sure. Why doesn't the enzyme already break down the milk? Am I making this stuff up? You can go to the dairy section and buy a lactate product, right? Yeah, I got nothing. It's possible that they've formulated the enzyme in such a way that it's not active until it gets in your guts. Your stomach has a pH that's really acidic, and enzyme activity is pH dependent, so that might be the issue. I'm waving my hands here, so I don't know. What else? Okay. Well, let's now talk glucose, blood sugar, and diabetes. As I told you before, glucose is an aldehyde, and aldehydes are reactive to nucleophiles. Now, for the most part, glucose exists in this cyclic form, but there's always some of the open-chain reactive aldehyde that's present. And I want to show you what can happen when that aldehyde encounters a nucleophile. Your body is full of nucleophiles. In particular, a group that's nucleophilic is an amino group, and many proteins have a primary amino group on their surface. For those of you that know anything about amino acids, this is the lysine side chain. And we're going to put that on a big circle that's going to represent a protein. Perhaps an enzyme, perhaps a structural protein. For our purposes, let's say it's hemoglobin or HB. But we're going to abbreviate that whole amine as R. And thankfully, we're going to abbreviate glucose with another R. Okay? So what happens when the amine encounters the aldehyde? Well, the amine is maybe not strong enough to attack the aldehyde without the aldehyde being protonated. So we're going to show the aldehyde getting protonated. There's enough hydronium at pH 7 that there's at least a little bit of this present. So I'm not going to show that proton transfer reaction, but we will show the amino group attacking the carbonyl carbon to give you a tetrahedral intermediate. And because we've abbreviated so much of this molecule, I'm hoping it's easier for you to see the connection between what I've just drawn here as an intermediate and something that we saw previously. So I'm going to jump up real quickly. We'll come back here. But I'm going to jump up and copy a previous intermediate from acetal formation. Yeah. What we've drawn here for the amine attacking the carbonyl carbon should look exactly analogous to this intermediate from acetal formation. The only difference, see, notice the OH group, notice the carbon bonded to two oxygens, here's the OH group. The only difference is instead of this methanol having added, the amine added. So I don't want you to see this as a separate reaction. This is exactly the same reactivity, it's just the players are different. So, as before, you remember that we said that the methanol was a good leaving group. Here, this amino group is positively charged, and it's a decent leaving group. If it left, we'd go right back to starting materials, but as we have done before, we can use the conjugate base of our acid catalyst. Perhaps this is just water, perhaps some enzyme group, to remove the proton. I don't like where that arrow went. The arrow needs to point to the nitrogen. We can remove the proton to generate the following intermediate, where now nothing is a good leaving group. And this should be exactly analogous to what you saw above with the hemiacetal intermediate. You see the analogy? The only difference is instead of methoxy here, we've got the amino group. Now, because that's an amino group instead of a methoxy group, we're not going to call that a hemiacetal. Your text calls that a carbonyl amine with an amino group and an alcohol attached to the same carbon. You could call it a hemiaminal. Now, in acetal formation, we wanted to get rid of the water, so we can use an acid catalyst to protonate the OH group, thereby turning it into a good leaving group. Now it becomes water. That group can leave as neutral water. And as we did before with acetal formation, we can kick electrons down and kick water off to generate the following ion. Let's see. With a positive formal charge on nitrogen. And water was our leaving group. Now, the analogous structure in acetal formation was this oxonium ion, which was positively charged because the oxygen was bonded to three things. Notice that nitrogen's from a different column of the periodic table. It comes with a different number of valence electrons. Nitrogen is only positively charged when it's bonded to four things, not three. Unlike the oxonium ion, there is something we can do with this ion that doesn't involve attack of a nucleophile, and that's simple proton transfer, which is really fast. And so before anything else happens, the conjugate base of our acid removes the proton, and we're left with this neutral product where a nitrogen's bonded to three things. And this neutral product is called an imine, I-M-I-N-E. Nobody says imine, so because it sounds like you're telling somebody what you mean. So we say imine. It's kind of tough to say, but imine. It's not an amine like A-M-I-N-E, it's an imine. And instead of calling the previous ion an oxonium ion, we're going to call it an iminium ion. The difference between oxonium and iminium is that the iminium has a proton on it that can be removed to give us a neutral product, and that's not a possibility for this oxonium ion. Okay, so now let's go back to what these R groups are, because we're talking about high levels of blood glucose. This imine is a new functional group you haven't encountered before. It's useful in the lab, and we'll use it all the time, and I'll show you some things a little bit later on for what we're going to do, how we can use imines. But I just want to make the point that what we have actually done is we have taken the glucose molecule and through this imine we have linked the glucose molecule to our hemoglobin on a lysine side chain. Now, for hemoglobin, this may not matter too much for its function, but you can imagine other enzymes where that nitrogen might be supposed to do something important. Remember that lysine side chains, as I told you earlier, are normally positively charged at physiological pH. Now that nitrogen's neutral, and instead of just having protons on it, it has this whole big carbon chain. That can affect the function of various enzymes and structural proteins, and that modification of nucleophiles because of high blood sugar is a cause, one of the causes of the various symptoms that are associated with diabetes. If you have tissues where nucleophiles are key for function, like in the eyes, having excessively high blood glucose can lead to blindness, it can lead to kidney damage, it can lead to neuropathy in the extremities. All of that because your sugar's too high, so you're making imines everywhere. Biologists and biochemists will often call imines Schiff bases. I remember when I took biochemistry, my professor started using Schiff base. I thought he said shift base, and I'm like, what the heck is that? When you hear that term, they're using an old biology term for imines. And if you want to be that person, that student, you can raise your hand and say, actually, it's called an imine. And then he can say back to you, actually, in my class, we're going to call it a Schiff base. Incidentally, if you are diabetic and you go into your physician and they take a blood sample, what they're looking for in terms of managing your diabetes is your hemoglobin HbA1c. That's this glycated product, and they're looking for, the more of this you have, the higher your glucose has been over time. Red blood cells are recycled at a slower rate than just every day. So this is a long-term measure of blood glucose levels instead of just measuring it in serum right at the moment. Yeah?
Are there a number of those glucose molecules bonded around the hemoglobin?
Could there be more than one? I think so. I don't know how specific it is. My sense is that I don't know. There are easy ways in terms of an analytical chemistry to determine how much hemoglobin, whether you've got one glucose on or multiple glucoses. So I'm not sure. I don't have a good answer for that. My sense is that this is non-specific. This isn't enzyme catalyzed. It just occurs because aldehydes are reactive and you have plenty of hydronium present, even at pH 7, to catalyze the reaction. In a less sinister sense, this is called glycation, and sometimes you'll hear people talk about glycated end products. This results from chemistry that happens after you do this, but forming imines and then stuff that happens is actually also associated with the lovely golden brown crust that forms when you're cooking bread or other things. It's called the Maillard reaction, but it involves first imine formation. So when you're baking bread and it tells you to put it in the oven and wait until the crust is golden brown, you're waiting for this to happen and then some other downstream stuff too. Okay. Yeah.
For pre-diabetics, is that looking at the HbA1c as well and just having it not quite as high?
Is for pre-diabetics is looking for HbA1c the same thing? I think yes, it's a longer measure of blood glucose, and you can look for that in anybody. Like even I am not diabetic, but when I do a blood draw, they're still looking at my HbA1c, and I think they would notice it first there. I don't know because I'm not a physician, so don't take any of that as gospel. Yeah.
There's no like alpha or beta when we keep it as a double bond on the original like glucose open chain?
Right, that's a great question. There's no alpha or beta when there's a carbonyl here because there's no stereocenter. Yep. All right. There's more to say about imines, but I just realized there was something I forgot to do with acetals. I told you that acetals are important in sugars, but I want to show you just in the last little bit how you can use an acetal as a protecting group. Okay, so we are shifting gears a little bit away from the shift bases. Shifting, shift. Good, good. Groaning is the appropriate response to that dad joke. So suppose you wanted, we can use acetals as protecting groups for aldehydes. Suppose you had this ester with this aldehyde group, and suppose you wanted to I'll use the same example I used in the first hour. Suppose you wanted to convert the ester into the tertiary alcohol where two of the same groups are attached to that carbon without touching the aldehyde. So your first inclination might be, oh sure, this is easy. Let's just use an organolithium reagent. The problem is organolithium reagents can react both with esters and with aldehydes. And so likely, instead of the desired product, if you just try to do this reaction directly, likely you make not only the tertiary alcohol, but you convert the aldehyde into the secondary alcohol, because lithium reagents are not selective for esters over aldehydes. So if we wanted this desired product, what we would need to do is change our strategy. We have to convert the aldehyde into something that is not reactive as an electrophile before we expose this molecule to the organolithium reagent. So one of the things we can do is to form an acetal out of the aldehyde. I'm going to use this alcohol. You don't have to use this particular alcohol. You could just use a single alcohol instead of this diol. The diol is useful because it has both OH groups that are going to be involved in the acetal in the same molecule. We're going to use some acid in organic solvent. I'm choosing para-toluene sulfonic acid because that's what we've done before. If you make the acetal here, you end up making a 5-membered ring with the carbonyl carbon. Now that looks different, but again, abbreviate and you can see the analogy to your previous acetal. Okay? That acetal is not a good electrophile. There's no pi star for a nucleophile to attack, and the carbon-oxygen antibonding orbitals are high enough in energy that a nucleophile won't hit it. There's no acidic protons there, so now you can do your organolithium reagent to bring in that carbon group. Your ester survives unscathed, but you've made, your aldehyde, your acetal survives unscathed. Your ester gets attacked by the organolithium reagent to give you the tetrahedral intermediate, and then the oxygen gets kicked off and so on, like we've talked about before. You get the tertiary alcohol, and then if you want to liberate the aldehyde, then you just use hydronium, some aqueous acid, and the acetal falls apart. So we can use the acetal as a second example of a protecting group to get selectivity out of situations where there normally isn't any. Another interesting point is, suppose you had a diol that you wanted to protect, you could use the alcohol as a protecting group for a diol. You could use the aldehyde as a protecting group for the diol. All right, questions about that? Yeah.
Is there a reason that the two alcohols don't go on the other ketone?
Okay, yeah, so is there a reason that we don't, that these conditions don't mess with the ester?
Yes.
The ester is stable enough that if you keep the concentration of acid low, you can do the reaction on the aldehyde and not on the ester. That's hand-wavy because in some ways you wouldn't know that. We will do a reaction later on where we react esters with acid. So the idea is presumably if you don't add a lot of acid, you can protect the aldehyde without hitting the ester.
Can I ask you a few questions?